Scientists have discovered new layers of ice buried a mile beneath Mars's North Pole, which are the remnants of ancient polar ice sheets and could be one of the largest water reservoirs on the planet. A team of NASA scientists made the discovery using measurements gathered by the shallow radar on NASA's Mars Reconnaissance Orbiter. Shallow radar emits radar waves that can penetrate up to 1.5 miles beneath the surface of Mars. The findings are important because the layers of ice are a record of past climate on Mars in much the same way that tree rings are a record of past climate on Earth. Studying the geometry and composition of these layers could tell scientists whether climate conditions were previously favorable for life. The team found layers of sand and ice that were as much as 90% water in some places. If melted, the newly discovered polar ice would be equivalent to a global layer of water around Mars at least 1.5 meters deep. Finding this much water ice likely makes it the third largest water reservoir on Mars after the polar ice caps. Scientists think that the layers formed when ice accumulated at the poles during past ice ages on Mars. Each time the planet warmed, a remnant of the ice caps became covered by sand, which protected the ice from solar radiation and prevented it from dissipating into the atmosphere. Scientists have long known about glacial events on Mars, which are driven by variations in the planet's orbit and tilt. Over periods of about 50,000 years, Mars leans towards the Sun before gradually returning to an upright position, like a wobbling spinning top. When the planet spins upright, the equator faces the Sun, allowing polar ice caps to grow. As the planet tilts, the ice caps retreat, perhaps vanishing entirely. Until now, scientists thought that the ancient ice caps were lost, but the study shows that in fact significant ice sheet remnants have survived under the planet's surface, trapped in alternating bands of ice and sand like layers on a cake. The study provides new important insights into the exchange of water ice between the poles and the mid-latitudes. The total volume of water locked up in these buried polar deposits is roughly the same as all the water ice known to exist in glaciers and buried ice layers at lower latitudes on Mars, which are approximately the same age. Studying this record of past polar glaciation could also help determine whether Mars was ever habitable. While slowly climbing the slopes of Mount Sharp recently, Curiosity rover discovered large deposits of carbon locked away in carbonate minerals. This find suggests that the red planet was once warmer and habitable. Carbonate minerals form when carbon dioxide interacts with water and rock, making them an important marker of past environmental conditions. Scientists have spotted these minerals before on Mars, by rovers on the ground, orbiters above and even in Martian meteorites that fell to Earth, but Curiosity's latest data adds exciting new details. It tells us that the planet was habitable and the models for habitability are correct. The minerals found by the rover likely formed in extremely dry conditions through chemical reactions between water and rock, followed by the process of evaporation. This process points to a time when Mars had a thick enough atmosphere rich in carbon dioxide to support liquid water on the surface. However, as the atmosphere thinned, that carbon dioxide would have begun turning into stone. One standout mineral in Curiosity's new discovery is siderite, an iron-rich carbonate found in surprisingly high amounts between 5 and 10% by weight alongside salts that dissolve easily in water. The broader implications are that the planet was habitable up until this time, but then as the carbon dioxide that had been warming the planet started to precipitate as siderite, it likely impacted Mars's ability to stay warm. What makes this find even more fascinating is the presence of iron oxyhydroxide in the same deposits. These minerals suggest Mars may have once also had a functioning carbon cycle similar to Earth's, where some of the carbon dioxide locked in rocks eventually made its way back into the atmosphere. By comparing Curiosity's findings with orbital data, scientists believe similar layers across the planet could have trapped up to 36 millibars worth of atmospheric carbon dioxide, enough to dramatically change Mars's climate. Hundreds of individual lava flows are seen here frozen in time on the flanks of Olympus Mons, the largest volcano in the solar system. The image taken by the Mars Express focuses on the southeast segment of the giant volcano, which towers some 22 kilometers above the surrounding plains. This is more than double the height of Mauna Kea, the tallest volcano on Earth at 10 kilometers when measured from the oceanic base to the summit. Like Mauna Kea, Olympus Mons is a shield volcano with gently sloping sides that extend outwards at low angles. But unlike other shield volcanoes, it has an abrupt cliff edge or scarp separating it from the surrounding plains. The scarp circles the entire volcano, in places reaching 9 kilometers high. It was likely formed during a number of catastrophic landslides on the flanks of the volcano, during which the resulting debris was transported several hundred kilometers beyond the extent of this image. Lava flows cover the base of the volcano, punctuated by a handful of pointy and flat-topped blocks that were either rotated or uplifted during the collapse. The transition from the towering heights of the volcano down onto the flat lava plain at the base of the scarp can be easily seen in the image, and extensive networks of narrow, overlapping lava flows are proof of an extremely active volcanic past. The lava, long since solidified, once spilled down the natural contours of the volcano, spreading out into broad fans as it reached the scarp and plains below. Flows that ended before reaching the scarp did so with rounded tongues as the lava cooled and crept to a stop. Some lava flows are bounded by steep channel walls, while others were contained in lava tubes. Zooming into the top left portion of the flank in the image reveals one example of an ancient lava tube, its winding track partially exposed in channel segments where the roof of the tunnel has since collapsed. The chaotic lava flows on the flanks provide a stark contrast to the smooth plains seen surrounding the volcano. Here, only two prominent features are visible: a wrinkle ridge in the lower center of the image, which formed as lava cooled and contracted to buckle up and distort the surface, and a channel system that branches out into a horseshoe shape. This channel was likely carved by lava, but water may have once flowed here too. The occurrence of only a few small impact craters in this scene shows that it is relatively young compared with more heavily cratered regions elsewhere on Mars, because the older the surface, the greater the exposure time to impact events by asteroids or comets. Furthermore, by looking at how the lava flows overlap, one can determine their relative ages. Those that lie on top, cutting through and overprinting other flows, are the youngest. For example, the vast lava plain surrounding the volcano truncates the majority of the lava flows extending from the flanks, suggesting it is younger still and that it originated from a location outside of this scene. The volcanic region hosting Olympus Mons and several other large volcanoes is thought to have been active until tens of millions of years ago, relatively recent on the planet's geological timescale that spans 4.6 billion years.